we better get going so we don't run over. Gene will be mad. Okay, everyone, good afternoon. We are in session 2. We're going to begin here. We have our panelists up here, and we do have one remote Zoom. He'll be the last presentation. And just a note, or because he is in virtual on this, we're going to hold all questions till the very end for all 3 of the panelists, okay? Just so he can listen in. So for our first speaker, the session 2 is developments in site investigation, characterization, and remediation. Our first speaker is going to be Sarah Meyer in regards to real-time forensic evaluation of PAHs during sediment investigation in urban waterway.
Thanks, Gary. I'll start by acknowledging contributors to this work at Ramboll, Eric Hritsuk, Lauren Brown, and Michael Bock, and with WEC Energy Group, Patrick Kenny. So I'm going to tell a story about some near real-time forensic work that we did on an urban waterway and actually the Chicago River, which we heard Marcus talk a little bit about in this morning's sessions. I've talked about this work in different parts of the Chicago area waterways multiple times at conferences, and people rarely ask me about the technical aspects of the work. They always ask me about the Chicago rivers. So I wanted to start with a little story on the background of the Chicago rivers. If you're not from the area or really into civil engineering, you might not know this story of this. So the Chicago area waterway system, CAWS as it's known, and then I'll roll in the MGP work that we've been doing on facilities adjacent to the CAWS. So the CAWS is actually over 76 miles of waterways in the Chicago area. They're all navigable. They also include locks and dams and ports and marinas. There are many sections of the waterway. The 2 that we've been working on since about 2007 are the north and south branch of the Chicago River and the Chicago Sanitary and Ship Canal. The majority of CAWS is man-made. If they were natural features at one time, they've been straightened and deepened for navigation and also to convey wastewater away from the city. And actually, the entire system is controlled by these locks and dams. The level of Lake Michigan is kept several feet higher than the Chicago area waterways, such that water from the lake will flow into the waterways and eventually to the Mississippi River. So it's a managed system. This is a schematic of the Chicago rivers, north and south, and the Chicago Sanitary and Ship Canal. And we've been working on 9 MGPs in this area. Here on the north branch, MGPs 1, 2, and 3, they're all surrounding a historic feature, Goose Island. That's on the north branch. This here is what's known as the main stem of the river. Down here on the south branch, MGPs 4, 5, 6, and 7. And on this feeder branch, which is known as the South Fork of the South Branch or Bubbly Creek. We also heard some talk about that earlier today. There was an MGP located there. And then furthest to the west and farthest downstream at this point is MGP 9, which is on the CSSC or the Chicago Sanitary and Ship Canal. Typical conditions along the CAWS today. It's a very urban waterway, a lot of industrialization developed in the city of Chicago around these waterways. Today, these are modern photos. You see, this is an auto fluff yard right up at the seawall. This is a concrete cement manufacturer with materials barged in and docked here. And this is part of the combined sewer system. These are CSOs that lead right into the CAWS. These are all over the city. and quite a few in the areas that we work in also. So there's a lot of potential sources of contamination to these waterways other than MGP. So this farthest west reach of that image I showed you before, the Chicago Sanitary and Ship Canal, this is the engineering marvel that people love to talk about in the city of Chicago when they talk about the rivers. This is entirely man-made, and it was opened in 1900. Its main purpose was to reverse the flow of water from the North Branch out into Lake Michigan to water moving away from Lake Michigan. Lake Michigan was the supply of drinking water, still is, for the city of Chicago. And in heavy rains, Chicago is very shallow, has a shallow aquifer. It was very swampy at one time. Sanitary waste would get pushed out into Lake Michigan and contaminate the drinking water. So it was a public health issue that led to this engineering marvel that is the Chicago Sanitary and Ship Canal. This is, if you ever want to see some great photos of this, the Metropolitan Water Reclamation District of Chicago has a great Twitter feed. And these images are from there. Twice a week they put up photos from their archives. This is one of them. It's a steam shovel in 1895 working on that canal. This is another photo from that Twitter feed in the 1890s, construction of the canal again. When all was said and done, it's almost 34 miles of canal connecting Lake Michigan with the Des Plaines River, which eventually empties into the Mississippi River. It's 24 feet deep on average and about 200 feet wide. And this schematic, again, is showing how flow changed once that canal was open for business. Before opening of the canal, we had the North Branch here at number 1, flowing south, the South Branch here at number 3, flowing north and east, and both of them coming together at the main stem flowing out into the lake. After opening the canal, the North Branch remained unchanged, water still flowing south, but now the main branch is flowing west from Lake Michigan. The two of them join the South Branch and flow west into the number 4, the CSSC, and on to the Mississippi. To put that in perspective of when these MGPs were operating, there's a basic timeline of what was going on then. Chicago was incorporated as a city in 1837, and by 1850 they had begun construction of the combined sewer system. The first 8 MGPs were opening between 1862 and 1897. And you recall in 1900, that's when the completion of the CSSC was occurred and flow changed toward the westerly direction. And then in 1911, those MGPs begin to close. The largest of those and the most western MGP, number 9 down on the CSSC, didn't open until 1921. And that was in operation until about 1971, and by that time, all those MGPs were closed. Okay, so I'm going to talk now about that MGP number 9, the one farthest west, down on the CSSC. Just a reminder again, here it is down in the left-hand corner, farthest downstream. This one was built in 1921. At 260 acres, it was the largest MGP that the operating company had built at the time, and actually is one of the 2 largest built in the United States. It was producing 3 types of gas: coke oven gas, carbureted water, and reformed natural gas. By 1956, it was really used as a peaker plant when grid demand was high in the city. After the plant was closed, the parcels were divided up, most of them going to third parties, although the gas company still owns several of those parcels. Today, land use on and around that facility, here it is here, outlined in black. Here we've got warehouses, cold storage, transportation, logistics, trucking, pipelines are some of the owners of that property now. In the surrounding areas, the gray and the peach here are manufacturing or planned development. It's a very industrial area, but you can see how close the yellow or the residential areas are to this location. So, getting to the problem here and why we developed this forensic analysis. Each of these MGPs, including number 9, is enrolled in the Superfund alternatives approach. And so the goal is to run them through remedial investigation, feasibility study, and move to remediation. And the first step of that is the investigation and to define the extent of contamination in the waterway. And we started that field investigation in 2017. We investigated about a mile along the adjacent to the former MGP in the CSSC. I think there's about 140 boring locations shown there. And we found MGP-affected sediment both at the upstream and the downstream ends of this study area. Upstream is off to the right, downstream is off to the left. So we had further work to do to find the edges of the effect of the MGP in the sediment. That was made a lot harder by these CSOs, these combined sewer outfalls that are located in the area. There are 20 of those along the CSSE, 11 of which are right in the area of the former MGP. These are some photos of those. They're very large. And they've carried combined storm and sanitary discharge into the waterway for a long time. That's a whole other story, but we know it's been conveying pollutants to the waterway just as a part of the urban environment. In addition, there are nearby facilities that have also had the potential or documented contributions of pollution to the waterway, and some of those are right here, right in the area of the MGP. There's right next door creosote and refined tar production that's still in operations today, chemical and cement production in the area, waste management. There's a former coal-fired power plant on the other side of the facility. So a lot of potential sources of pollutants to the waterway right in the area of the former MGP. So to tease out what pollution was possibly related to the MGP from that related to all these other sources in the area, we developed this solution. And it started with another investigation. This we did last summer, and we installed another 20 borings in the sediment, and this time we went almost 2 miles both up and downstream of the site with additional borings. We also ran those in addition to total PAHs, alkylated PAHs, metals, and et cetera. We did collect samples to evaluate NAPL mobility. And while we were out there, we investigated surface water conditions and did some shoreline reconnaissance that's helpful in establishing the conceptual site model. To give you a frame of reference for the concentrations of total PAH we're talking about in these waterways, in this investigation, the range of values we documented were 2.8 over 43,000 milligrams per kilogram in sediment. And this is not out of line with what we saw on both the North Branch and the South Branch previously. We have established a background concentration, or we call it ambient in this case, of about 214 milligrams per kilogram. That was up on the South Branch. We're using that as a bit of a benchmark for background in this area. So we do have concentrations that are greatly exceeding that number. And these are all up and down the 2020 study area, so not just near the MGP, but as far upstream as almost 2 miles. So our approach to the teasing out whether it's MGP related was kind of a classic forensic study of the chemistry of the PAHs, but we did it a lot faster than we had done in the past. In the past, we had mobilized the field, collected all the data, demobilized, and did the desktop study, which took weeks or months to come up with the forensic story. Is it MGP related or not? In this case, we turned that weeks or months into a 5 to 7 day cycle that we implemented while we were in the field so that we could use the forensic information to make field decisions. So we started simply by collecting borings in the field and logging those and sending samples into the lab for a quick turn analysis for alkylated PAHs. As soon as the data was available, imported that. We had developed an R script to do the forensic evaluation and place the new samples into likely source, related source buckets. And we were able then to use that data to define our next steps in the field. In other words, were those last samples related to the MGP or not? Did we have to go further? So the forensic methods we used were multiple lines of evidence. We first developed a library, and this included samples from literature. Also, we had actual samples of product from the MGP that we collected in the upland. There's a related upland remediation going on, investigation and remediation at the same time. And then we had these ambient samples from upstream in the South Branch. So we were able to compare the investigative samples to this wide variety of library samples. And then we also did a hierarchical cluster analysis and principal component analysis, and all those analyses converged on a few results. These are the PCA plots, principal component analysis. On the left, you have component 1 plotted against component 2, and on the right, component 2 plotted against 3. And then you'll see the cluster colors from the HCA. The idea here is that the colors are falling together on these plots. So the yellows are clustering here, and over here they're clustering here, which means that we've put them in the right buckets in both the HCA and the PCA analyses. So we've got like samples grouped together. And the outcome of that analysis brings us to this, which is a little more of a tactile interpretation of the data. Those 10 clusters we reduced to classifications of samples. And so each sample fell into what was its likely source of PAHs for that sample. And those we found were background related, or PAHs related to distillates, or they were a mixture of PAH sources without an MGP signal, or they were a mixture with a possible MGP signal, or they just outright looked like they were from an MGP. So what you're looking at here on this hanging garden plot, I'd like you to focus on the yellow or the MGP symbols down here. Along the x-axis is river mile. On the left here, this is the farthest downstream boring. On the right here, this is the farthest upstream boring. And right here, this is depth. So this sample is from the surface, and this is down to about 15 feet below mudline here. So you can see MGP-related samples falling in this area. And then on the upstream end, we have what we call an MGP void, right? We no longer see the MGP signal in 3 borings here. And on the downstream end, we see a void immediately downstream of the MGP, and then the MGP signal picks up again. So we felt we had identified the extent of the MGP influence, but we had a little more work to do to figure this out. This is those voids in plan view. So the MGP is in the center here where the high density sampling is. Here's the downstream void, and the yellow MGP picks up again. And here's where the upstream void is. So what could be causing this return of MGP signal downstream of the void? We were able to find in literature references to, and it's existing today still, a crude tar processing plant located right here. Has a terminal operations here right on the waterway. This plant was built in 1920, and it converts crude tars into liquid pitch and other tar-related products. This facility has documented releases into the waterway that we were able to locate. Here's a list of 16 of those just from 1990 through 2005. One of which here in 1995 was a 17,000 gallon spill of coal tar into the waterway that US EPA got involved in the cleanup of. Now this material, what we saw in the forensics, looks like it could be from an MGP, but it actually doesn't match the exact signal of our source samples from the upland MGP number 9. So we were submitted in the RI that the downstream samples where the MGP signal reappears are related to this facility. And upstream, we have an area where the MGP signal dies out, but we have about 1.5 miles upstream of the facility where we saw an MGP signal. And in our CSM conceptual site model, we are attributing this to, at least partially, to this what's called the collateral channel, which in the early 1900s was an open sewer, basically, for the surrounding area, where stormwater, surface water runoff, sanitary discharge, whatever needed to go away ended up in this channel. This here is a picture today of that channel. It's a known contributor to poor water and sediment quality in the area. So historic discharge from this channel is a contributor to what we're seeing upstream here of the facility. And then I'll wrap up just by saying we're still working on the site. It is part of that portfolio of 9 MGPs in the area, and they're all, we're working on them all in parallel. We have submitted the RI report for this MGP number 9 up on the north branch. We're actually moving into the feasibility study now. That's setting precedent for what's happening at the number 9. And we're heading back into the field on the south branch probably in 2022. And so we're building on information we gather from one of the groups, MGP groups, to another. And that's all I have prepared today. I'll be happy to take questions when the panel's finished. Okay, thank you.
Thank you, Sarah. Okay, our next speaker is Benjamin Clement, our GCP Senior Geologist at Burns and McDonnell. It's in regards to high-resolution site characterization and rapid implementation of combined remedy for multiple parcels with evolving property usage. Say that 3 times fast.
Long one. All right, so yeah, our agenda here, talk a little bit about the background of the site, some of the high resolution site characterization components that we used, a little bit of remedy evaluation selection, talk about some of the pilot testing we did that is just finished up, implementing some of that, and then the conclusions. So this site is in central Illinois. You see where I've got the site labeled there. Our client actually owns all of that property that is in blue here. Surrounding property usage, mostly commercial industrial. They have a substation. There's warehouse facilities here, wholesale flower shop, parking lots, old warehouses down here. At this time, when we started investigation, the closest residential property is down here a few blocks away. That'll be worthwhile noting later in the presentation. what they use the site for now, it's a gravel lot. They have a small gas regulator station, lay down yard for some of their utility crews that work in the area. So this just gives you an idea of some of the former existing site conditions here at the site. There was just one holder here in the center. Then there was the production building here, the small tar well, a few below ground fuel oil tanks. And then in red here, this is where that existing gas regulator station is here. So back in 2001, soon after they had started investigating the site, they had done an interim removal action. And at that time, the building was still in place. So they had done some investigation and found, yeah, there was a holder here and there was some nasty stuff. So let's dig that out. Kind of just focusing on the property itself within the site boundaries. So they dug down to the holder base, about 10 feet right next to it, and sloped up the grade. Basically got what was easy, what was accessible at the time. Lot was left in place, and they'd been investigating for 20 years. So about 2018-19, we embarked on our high resolution site characterization. These are some of the components. I'm not going to show data for all of these just because it would take up too much time, but we're going to talk about ESS, Targhost, ECHPT investigation, combined with some of the discrete analytical sampling, and yeah, a couple shots of some three-dimensional visualization tools, and then use of risk assessment kind of combined with all of those things. So for those of you that know or don't know about environmental sequence stratigraphy, it's the idea of kind of looking at the depositional setting. How did the sediments get put there, and kind of knowing what that the depositional fabric is, to having an idea both regionally and then very locally, so you can be more predictive in where you would expect to see contaminant migration, where you'd expect to see lack of contaminant migration. And so this setting here is in a till plain here, like I said, in south central Illinois, kind of on the the lower extent of that glaciation that occurred. And then this here is kind of an inset that just shows you how dynamic deposition can be around a glacier. So you've got some of those materials that are deposited right beneath the glacier. You got stuff that's held within the glacier that then is deposited as the glacier retreats and melts. You've got some of these higher energy areas with streams, emanating from the ends of the glacier. So kind of having an understanding of how all those sediments could be deposited in this overall depositional environment can give us an idea of explaining what we are seeing and helping us predict and being more efficient in the data that we can collect. So this here on the right is a Targhost EC log, and just kind of shown here how you can correlate some of the field observations from conventional borings that you always want to proof these with. But something that we were able to do here was, and I've seen it work in some settings and others it doesn't correlate as well, but the EC really correlated well with the different types of depositional stratigraphic units that we're seeing at the site here. So saw a fill that was highly variable near the top. Then there was a loess where we see the EC have a little bit more clay content. And then really the zone that's most important here to look at that was really correlated well was this more permeable unit here that had sands, gravels in it. And that's, as you might expect, where you're having more of your contaminant migration, where you see, of course, all your napples and your tars were within this coarser zone. And then beneath that, as you see your clay content increasing here, the EC creeping up, saw two different basal tills that were much finer, higher clay content, lower hydraulic conductivities. So this was kind of one of our tools when you're able to collect a high density of data and then proof those in some of your conventional borings, collect targeted analytical samples, and then use the high res data to model it a little bit better. Of course, down here we also saw something why you want to have plenty of borings that you can confirm what look like hey, do we have impacts all the way down here? No, it was actually this peat unit that was observed at multiple locations across the site. So that was just something to confirm, was this basal till really confining the NAPL, or were we actually, seeing it down here? And in all cases, it was always observed to be just a unit of peat. So then this is kind of that same log that we looked at here for a different boring, but then marrying that with some HPT logs as well. And so something that we see here again, you see that lower EC magnitude indicative of the coarser sediments. And what we are seeing within that zone is that really most of the flow is within only half of that zone. So while the EC was good for really correlating those contacts, having an idea of what that the mobility of that unit was something that you could figure out with the HPT. And then so we produce something like this that's a cross section, and so we're able to take the response, the EC response data, help us really make those contacts. Whereas, if you're advancing a lot of conventional borings, obviously it takes a lot more time, money, etc. So going to the left of the axis there, you can see where there are higher Targos responses. That's that purple, and then where you see the pink here moving to the right of that axis. That is the electrical conductivity data. So again, we found we had really good correlation with these units, with the EC data, and that really defining these contact, which was big for getting regulatory buy-in on the characterization and then the remedial planning for this site. So unfortunately, I didn't have a 3D model to rotate up here, but this was something our client had placed a high value on this. They're able to share this with their internal and external stakeholders, where you can show people that aren't environmental professionals, kind of different aspects of what's going on the site. Picture paints 1,000 words. So just kind of a couple snapshots I took out of one of the 4DIM models, but this is those Targos responses that we're seeing. So you see we did have a fair amount of migration to the north of the site there. And then this area here is really an area of data that was not there because that's where the holder floor is. You can get Targos locations in there, but see we delineated it on the southern boundary here at the time of that investigation. Now to the south here, at the time we did this, there was no access to do additional sampling on this site. So we evaluated a couple different remedies, excavation, in situ stabilization, and we had settled on trying a surfactant enhanced fluid recovery and in situ chemical oxidation to really target the only zone where there was a lot of remaining impacts within that kind of 15 to 30 feet below ground surface, where we're not really having impacts within that upper 15-foot zone. So some of the biggest advantages is we're going to be cost efficient to other alternatives. We're going to have to, dig up some of that area that had previously been remediated, backfilled with clean fill. There are a lot of utilities, especially under the street there, that was north of the site that clients really not interested in having to deal with. And, minimize the potential vapor emissions instead of opening all of that up. So there are some risks to, got to verify distribution effectiveness and that the chemistry is going to work, that you're able to actually achieve, recovery of that material and that you get down to the levels you need to be at. It is an option that was going to take the longest. And, you can have issues with daylighting when you're injecting a lot of fluids into the ground. So the conceptual approach, kind of touched on it here, was really targeting this zone with the coarsest material here. And these purple bars are where in the conventional borings that we actually saw NAPL. So the idea was, hey, let's target this zone, try and recover total fluids, desorb some of that NAPL, recover it in liquid form, and then follow it up in certain areas with in situ chemical oxidation treatment to get below a level that is what is the state defines as source material criteria. So got a couple slides that have some of the preliminary pilot testing data. The pilot test took about 4 weeks. We did a treatment area on each area of the site, and we did experience a fair amount of daylighting. Actually, it did seem to be related to those areas where there was previous excavation, previous disturbance in the subsurface causing some preferential pathways. We ended up then having to use a direct push injection approach rather than trying to make use of the injection wells that we had installed. One thing that we determined then was that the effective porosity that we had assumed going in was even less than was expected. So that's something that's going to be taken into account with a full-scale design. This is, one of the samples. SB7 here was sampled, almost 10 years ago now. And then, after our injection that was in April of this year, did a post remediation round of sampling. We did get, pretty good results on the reduction here. So I think that's all I wanted to talk about on this one. Another thing we learned, we got a recovery radius of influence of about 30 to 40 feet with a pretty low pumping rate of just a half GPM. These are 4-inch wells. So again, something that is going to take into account for the full-scale design and altering some of the assumptions for recovery durations, amount of wells that need to be operating at the same time. It's just a distance drawdown plot here. So that was part of this main site remediation, site characterization, pilot testing that was going on early this year in March and April. And in January, our client learned, hey, somebody's actually purchased this property down here. They're going to build an elementary school on it. So said, we need to get out here and we need to determine, do we actually have anything that extended on this property? The data that we had here seemed to look like it basically stopped, but we need to check all our boxes here. We wanted to do the right thing and make sure that they remediated this site in the event that there was anything on it. So went out and used soil borings, collected groundwater samples and soil gas from this property here, the square here. Everything was basically done on this site. These are just some locations that had already been advanced before this investigation. So tried to get really good coverage. At the time, the plan for the school property was that the building was actually going to extend as far up here is about 10 feet within that property boundary. So we wanted to make sure from the indoor air perspective that we had a lot of soil gas data to look at that pathway. So this is the cross section that appeared on the last slide here. This is the north side here, the former MGP plant property, and then here's where that school property extent was. And what we're seeing here again is that it looks like that basal till is really limiting, the contaminant migration of that DNAPL that we see down here that collects on this basal till surface within this ablation till. And so this is the one location here that was, within 5 feet of the property boundary that actually had some material down a depth that required remediation. So all of these white boxes here mean samples that were collected that met all of the residential standards. So again, you can see as you move to the south here, having defined this contact was was key for this project. So this is a water level map of this site and the surrounding area. Again, this is that MGP property. Here's that school property down to the south. So we kind of get some bi-directional flow. There are some sewers that run in both these streets that do appear to control some of that shallow groundwater flow direction here. And then the natural groundwater flow direction kind of in the direction of that glacier, that glacier push from the northeast to southwest here, where you may expect to see some of that groundwater flow is where we're seeing this from the site towards the school property. So they wanted to make sure, hey, we don't want to go clean this up and then, recontaminate this area because groundwater is flowing in that direction, with a VTEX plume. So we talked about a couple different alternatives. Was there barrier walls that we could put in here? There's a small amount of material that was believed to be excavated. And, after some conversations with the stake owners, the property owners, and the elementary school developers, they decided, yeah, I think we'd rather just try and dig out everything that we can from the property here and really make sure that it's as clean as possible. So went out then and did a pre-confirmation sampling effort. Previously we had just had these the investigation locations, these SBs, 56, 57 here. So those are the ones we did as the investigation with the soil, groundwater, and soil gas sampling. So we wanted to go out, make sure we've got all our bases covered for the data we're going to need to provide the state to get an NFR for the site. So you have a higher sampling density for that confirmation data. So we felt pretty confident that, hey, I think, right now, SB 57 and 59, those are kind of our clean samples. We really don't think it extends that far. So let's even get some more data from within that zone. And sure enough, really SB 56, that was the one where we had previously seen higher impacts. So we were able to basically reduce the excavation extent from this area outlined in red. It's previously, planned to be this entire zone here. We're able to reduce that. And they were able to then extend some of their remediation to the north. So this is in cross-sectional view, just what that plan looked like is, again, digging down to that upper basal till surface and then getting the ingestion 0 to 3 foot zone remediated across the entire school property. So then because we knew that there was a developer that was going to be building on this site, we also communicated with them and said, hey, what would you guys like to have backfilled in this place? Is there a way that we can help you get what you need with, what we're going to have to do anyways, putting clean backfill in our engineer barrier or whatever. So we got, their civil design details and worked that into part of our bid package for our client's contractor. So made sure that was, something that was more efficient rather than, them having to come out and dig it up twice to put in their subgrade that they wanted. So we talked about that's the reduction of that area that we were able to accomplish. So the client said, well, we're already out here, installing sheet piling to dig some of these deep impacts out. Let's see what we can also get done since we're saving some money here. What can we do? What can we extend to the north? Because we know we have impacts, going up to the main site. So we're able to, with all the data we already had, really key in for that upper basal till contact and, allow them to extend and increase the amount of remediation that they were going to be doing at this time and get it done earlier, put more distance between, what is still left in place on site and where we've got clean backfill going in. So that was about a 4-month duration project. They're in the middle of it right now. They're planning on getting that finished and turning this property back over to the elementary school contractor next month, I believe. And this is just a photo of some of the sheet piling that was going in and some of the excavation they're doing. But it was pretty rapid process from when we've got, hey, January, figured out that this is happening. You guys got to show us what data we've got here, get a plan together, do the field investigation in March, bid package out in May, confirmation sampling June, MOB July. They're still working on the components of the earth retention system and the deep excavation. They're on track for getting the school property back to the new owner before the end of December, which is what their construction timeline was. So, what really enabled us to do that was having that bulk of data early. That's really what enabled us to have such a rapid, bid package completion, having a good idea of the nature and extent of contamination, even though we hadn't been on that site yet, but knowing the geology, knowing the depositional patterns. And that was able to save, again, about $5 million from an alternative of what might be, digging up all of that area. So another thing was the proactive stakeholder communication, making sure that the school was on board with the remedy, even though, multiple remedies might meet state requirements, that they were happy with it, that we could help their contractor by getting some of those construction components completed for them. Again, just kind of, making, it as a show of good faith that you're working with the community. And that, ended up helping the schedule for getting that contractor, the property back in their hands earlier. And then again, going in, having an idea that we do think that, the delineation is tighter than the data currently show, and going in, collecting a little bit more data, allowing them to move some of that scope expansion up to the north and get more of the main site remediated earlier than they had previously thought would be. I think that's the end. So I think we've got one more, right? Thank you.
Thanks, Ben. Our next speaker is going to be virtual, everyone. We have Matt Geary, Technical Sales Manager for CETCO Materials. And his presentation today, Innovations in the Use of Organoclay and Surface Modified Clay for Manufactured Gas Plant Remediation. I'm hoping you're connected, Matt.
I am. Can you hear me?
We got you.
Fantastic. I will start sharing my screen. And let me know when we get the presentation up on the board. Can you see it?
We do have it.
Fantastic. Just let me know when you want me to jump in.
Sounds good. Perfect.
Well, thank you very much. And thank you everyone for coming to hear the talk today. I'm sitting here in not so sunny Philadelphia, and I'm quite jealous of all of you there in sunny Florida. Today, as mentioned, I'm going to be talking about innovations in the use of organoclay and surface modified clays for MGP site remediation. I would first like to thank my co-author, Anna Willett, PE. She is the technical sales manager for CETCO, and we worked on this together. Before I give the agenda, I did want to give a brief background as to the parent company of CETCO, and it is germane to the topic. The parent company is called Minerals Technology, Inc., a minerals mining company. We have just under 4,000 employees, just under $2 billion in revenue, and we're publicly traded on the New York Stock Exchange. But the operative word in the company name is Minerals Technology, Inc., a minerals mining company, and you'll see why that's relevant in just a moment. So here's the agenda. What I want to talk about today is organoclay, and in the bulk form and reactive core mat forms for remediation on MGP sites, and then give an introduction into fluorosorb absorbent for the remediation of PFAS. Now you may wonder, what does this have to do with MGP sites? We currently have projects that we've been brought into that we're working on that started out as MGP sites, and now they're looking to handle both PFAS and MGP type contaminants of concern. So that's really the tie-in here. So as I go through, I will talk about PFAS source control with one of these modified clays. And in that section, we'll talk about work that was done by the University of Texas at Austin, and also do a brief case study for a Canadian DND site, again, for in situ stabilization, or excuse me, stabilization that was recently completed. Then a summary, and I think that brings us to the end of the presentation, and we all can answer questions. Okay, we first have to start with bentonite when we're talking about these modified clays. And the reason for that, as I mentioned just a moment ago, the parent company is a minerals mining company, and as such, they own a significant portion to the mineral rights to the Wyoming bentonite in the Black Hills of Wyoming. Now, this is a very particular type of bentonite. It's a sedimentary deposit containing greater than 50% montmorillonite, and it's volcanic in origin. So CETCO, as I said, the parent company mines this bentonite material and turns it into all manner of finished goods, including the two remediation products we're going to talk about today. The first being organoclay. So organoclay is a modified clay that's had a long history of use on MGP sites. It's a manufactured absorbent media that's made by modifying that bentonite clay. The way we do that is we knock off the sodium cation from the bentonite, and we replace it with a proprietary organic media. Now, once we do that, the organoclay no longer shows the properties that you think of in regular bentonite clay. In other words, when it hydrates, it no longer swells and becomes impermeable. Now, since we turn it into organoclay, it becomes hydrophobic. It allows water to pass through it, but the organic modifier grabs the MGP waste, the PAHs, the PCBs, et cetera. The absorption capacity for the organoclay is 0.5 pound per pound. So it has a very high ability to absorb the contaminants such as PAHs, PCBs, the typical MGP type contaminants. One of the ways that we have used organoclay, especially for MGP sites, and what I'm referring to here is generally adjacent bodies of water to MGP sites, ponds or lakes or streams that have had the MGP contaminants of concern contaminate their sediments. Well, the way we've remediated those is with the reactive core mat. And what a reactive core mat is two needle punch geotextile fabrics that hold in place whatever the appropriate media is for the contaminants of concern. So in the case of MGP sites, oftentimes we'll be using organoclay inside this mat, sometimes carbon, but we have the ability to build these mats with fluorosorb for PFAS remediation and various metals removals media. As long as it's granule, we can get it in there. Now, some of the benefits of doing this is you get a known quantity of active media on every square foot. For instance, in the case of organoclay, a reactive core mat would contain 0.8 pounds per square foot. So with certainty, when you do your remediation and you deploy very rapidly and very economically this media over a wide area, it really helps with your modeling because you know your flux and your contaminant concentration, and now you know exactly how much active media you have in a given area. So it really helps to predict the life of any remedy you would come up with. So it's a real benefit when either capping sediments adjacent to MGP sites or upland wetlands or other upland caps on MGP sites. One of the other benefits you get if you deploy the organoclay in a reactive core mat is you get a very thin cap. I'll go back for a second. You can see it's only a 1/4 inch thick, but it has that condensed area of active media. So this allows you to put, generally speaking, a 1 foot, a minimum of 1 foot armoring layer or sand layer on top, as opposed to capping that has been done in the past where you're talking 2 or 3 foot layers of clean sand. That's a significant cost savings. Here's just a quick case study from a site that was done in Portland, Oregon. This is a site where NAPL from groundwater was contaminating a beachhead and a freshwater bay. So the NAPL got into the sediments and gas ebullition was happening. And as the gas, and I hope you can see on your screen the top left picture, as the gas bubbles came up and burst, it caused a sheen on top of this body of water. So the CETCO reactive core mat filled with organoclay was laid on the beachhead and out into the bay, into the sediment. And if you look at the lower left-hand picture, you'll see that the gas bubbles were still coming up after placement of the reactive core mat. So we know that we still had the flux, both of nutrients in the water as well as the gas. However, when the gas bubbles burst after the placement of the reactive core mat, we see that there's no sheen developing. So we know that the proprietary organic modifier is stripping off the contaminants as they run through the remediation. Here's just a picture of it being placed on a much larger body of water. And this is just to illustrate that it can be done in large scale, generally speaking off of barges. If it's not too wide, you can use come-alongs and other mechanical means to stretch it across a large body of water. Okay, so I'm switching now to Fluorosorb, but remember, everything that I say from this point forward, including the case studies on source stabilization and other methods of remediation, I'm going to be focusing on PFAS remediation. But if you should have a site or any of the MGP sites you're currently working on that are in the future asked to look for PFAS, the point we're trying to drive home here is that this Fluorosorb absorbent, which I will introduce in a moment, can handle both the MGP types of waste or types of contaminants that you come across, as well as the PFAS. So if you're working on a traditional MGP site, long-standing history of using organoclay for stabilization or capping. But if you're working on an MGP site that PFAS rears its ugly head, here's a solution that has recently been developed. So what is that solution? It's Fluorosorb, and Fluorosorb is yet another modification to our base bentonite clay. Only this time the modification is specifically designed for the absorption of PFAS molecules. So what you're looking at here, this chart, is a representation of the current grain sizes and current types of Fluorosorb that we manufacture, from Fluorosorb 100 to 400. And if you take a look at the Fluorosorb 100, that's our semi-powdered version of the product, and take a run down that column, you see that we list a lot of different physical properties, permeability, seed size. But I would call your attention to that row at the bottom for applications. Here for that Fluorosorb 100, our semi-powdered version, it's being used in situ stabilization and solidification, so source control. And it's also being used in diffusive barofiltration treatment systems to replace powdered activated carbon. The next column is Fluorosorb 200, simply the next grain size up. Again, we list the physical properties. And if you look at applications, here it's being used for pump and treat, source control for stabilization, and permeable reactive barriers. Fluorosorb 300 and 400 are mostly being used currently in ex situ pump and treat systems. 400, the largest grain size, is being used for highly mixed waste like landfill leachate and the like. So we'll concentrate here on the 100 and the 200 and move on to ways that they're being deployed. It's got a significant versatility in deployment, and this is a feature and benefit that can be of value because, as we know, on a lot of these MGP sites, you're dealing with all different sorts of media and all different areas that you have to clean up. So it can be used for groundwater and drinking water filtration. Drinking water, because it's NSF certified, that probably doesn't necessarily apply to most of these MGP sites. But it can be used as a standalone product or in pre or post treatment. Passive groundwater, the previous speaker was talking about putting in potential PRBs or cutoff walls. You could use the Fluorosorb product here. And again, the Fluorosorb product would handle the PFAS contamination as well as the PAHs and the other MGP type waste. Source zone control. We're going to show you a brief case study at the end of a full-scale source zone control project that was completed in Canada successfully. And then lastly, sediment capping. We already talked about the reactive core mat. We can fill the reactive core mats with Fluorosorb. Again, you'd get a loading of about 0.8 pounds per square foot, and you can very economically deploy it over a wide area very rapidly. This new Fluorosorb product outperforms other products with higher absorption kinetics, better absorption capacity, less effect from competitive absorption, and it can be used in conjunction with other products. It's fully commercialized, and it was launched as a product formally in May of 2019. Okay, slightly off topic, but related to the MGP sites, what we're going to look at here is some early comparison work we did carbon. Now, granted, we're looking at it in the ex situ format, but we're just trying to get a baseline for performance because we know that you might think of using carbon either for in situ stabilization or capping for whether it's MGP site waste or PFAS waste. So with that in mind, let's go over this brief comparison that we did at the very beginning of our development of this product, and we did this with the Colorado School of Mines. And what we were trying, at the time, what we were trying to gather is just information about if you use Fluorosorb as pre-treatment, how much longer could you make carbon or IX resin last? So with that in mind, Colorado School of Mines set up the lead lag columns you see listed here, with the first column being Fluorosorb followed by Fluorosorb, then GAC followed by GAC, then Fluorosorb followed by GAC, and lastly, Fluorosorb followed by IX resin. And here's the results. What we can tell you they were looking at was the sum, for the influent, was the sum of 8 major PFAS, and the total concentration there was 45,000 ppt. Further, we know that the action level for this particular project or this experiment was 70 ppt because this was a military site, and that's often the target value for a preliminary remediation. So if you take a look at the gray circles, that represents the breakthrough of the lead carbon vessel, and we see that it broke through at about 2,000 bed volumes. And the green diamond represents the breakthrough of the lead Fluorosorb vessel. It did not break through to closer to 8,000 bed volumes. So about a 4 times greater absorption capacity. And this is what we've seen in both in our pilot scale work, lab work, and now in full scale applications. When compared to carbon, we're looking at anything from 3 to 5 times greater absorption capacity. So I want to cover briefly why that is, or one of the reasons why that is, why there's this greater absorption capacity. And this slide is meant to illustrate one of the reasons, the main reason really. And if you take a look at the top, that represents the typical isotherm readout we get whenever we do batch testing with Fluorosorb. We get this unique shape to the curve of the data. There's an inflection point or a jog in it. And that's been consistent throughout all of the work that we've done. And we had a theory why that is. And these 2 images at the bottom are going to help me explain what our theory was and how we since have gone and proven that theory to be correct. So on the bottom left, what you're looking at is what the Fluorosorb platelets look like after we do the modification to the base clay. The platelets line up one on top of each other, and there's a spacing in between called the D-spacing. So our theory was that we're getting expansion in that D-spacing, allowing for greater absorption. So what we did is we measured the distance in that D-spacing on the image on the left prior to the inflection point. As PFAS was coming in, but prior to the inflection point, we measured the distance in that D-spacing. It was 25 angstroms. Then we allowed more PFAS to enter into the system and measured that despacing again after the inflection point, and then went up to 50 angstroms. So simply put, we can get more meat in the sandwich. This is not a swell. This is happening at the micro level. At the macro level, we know there's no swell, both from graduated cylinder work in the lab and now full-scale applications in the field. But this expansion that allows for the greater absorption of PFAS can also be a benefit in the field if you're doing source zone stabilization. And again, both for PFAS and for PAH contaminants that you typically get at an MGP site. So let's look at that, the use of fluorosorb absorbent for stabilization of PFAS in soil. As I alluded to earlier, some of the work that we did was with the University of Texas at Austin while establishing how well fluorosorb would work in this application. And what we did is we sent them some soil. Again, we're looking at a DOD site, so the action level for this experiment was 70 ppt. University of Texas analyzed the soil we sent them, and you can see that many of the PFAS molecules were above that action level. And now we proceed to what is the summary slide of the professor from UT's presentation. I can tell you that normally between those two slides, there's at least 10 or 15 slides talking about how the cores were set up and how the mixing was done. But for the purposes of our talk today and the time we have today, I'm jumping right to the concluding slide. Suffice to say that PFAS was mixed in various ratios to that soil I just showed you the analysis on. And they did US EPA LEAF method 1313 and 1316 to measure the PFAS, and then to measure the PFAS in that leachate. And that's what this graph represents. On the left, you're looking at increasing concentration of PFAS in the leachate after various treatments. And on the bottom from left to right, you're looking at increasing addition of Portland cement to the admixture. So if we start at the control, the gray line up at the top, that's with no treatment or 0% fluorosorb added. We see that from 3% Portland cement to 5% Portland cement, there was a reduction in the amount of PFAS coming out in the leachate. However, once you got past 5% Portland cement, the amount of PFAS in the leachate quickly started to rise, and not pictured here, but once you got more than 10% cement in the admixture, it became asymptotic and all of the PFAS came rushing out. So we move on to a low dose PFAS admixture, and that's the yellow line, the next one down. So if you look at 1% fluorosorb added to the mix, when you get to 5% Portland cement and 1% fluorosorb, they did achieve 1 point below the action level for this site. But after 5% cement with only 1% fluorosorb, again, the PFAS quickly started to come out. This is due partially to the increased pH that you'll get when the cement is added. Same thing with the control. As you add more cement, increased pH, sending more of the fluorosorb moving. The last thing about that yellow line, though, when I was speaking to the professor, he said, well, that's a shame, it didn't work. And I would beg to differ in that if you would have a site, say an MGP site that also has PFAS, that isn't going to be developed into anything significant, and therefore you don't have a very high unconfined compressive strength parameter, and maybe you have very low groundwater velocity, then you could possibly get away with a 1 or 2% fluorosorb mixture, which will take care of the MGP waste and the PFAS, and be a very economical mix design. But we know that there's many cases when there will be a higher unconfined compressive strength parameter. So that brings us down to the bottom line, the bluish purple line. Here we're looking at 5% addition of fluorosorb. And when you get to 5% fluorosorb and 5% Portland cement, what the experimenters called the optimal design, you're below that action level. But what's interesting is as you add, once you get to 5% fluorosorb, as you add more and more cement, it never went above that action level. So good news if you're looking at a site that you want to develop that has high rises or something that's causing a very high unconfined compressive strength or very high groundwater velocity where you want to get a lot of cement in there to cut down the hydraulic conductivity through your monolith. All possibilities now if you're looking at going as high as a 5% fluorosorb mix. Pardon me. So the University of Texas concluded that all PFAS were reduced to low concentrations for all mixed designs containing the fluorosorb 100, and that was regardless of OPC content. However, it was important to note that Portland cement alone was not effective in stabilizing the same constituents. And again, they said the optimal mix design was 5% Portland and 5% fluorosorb, although the contention from at least my perspective is that every site's going to be different, and so you would need to run treatabilities on any particular site that you have. All right, let's talk about this project I alluded to, a full-scale soil stabilization project. It's titled ISS, but it really should be SS because this work was done ex situ and then put back in the hole. But nevertheless, this was a firefighting training area at a military site in Canada. PFAS was detected in the soil and groundwater, and PFOS was the main target of the remediation. And again, the source zone treatment consisted of excavating all of the PFAS contaminated soil, mixing with fluorosorb. It ended up being mixed with fluorosorb, but you'll see in a minute the treatability that they did tested a variety of different potential admixtures. I should note that on this site there was also organic contaminants that would be typical to find on an MGP site. And so that was one of the reasons for choosing the fluorosorb. These graphs in the middle are just pictures of the various areas that needed to be dug, ex situ stabilization, and then put back in the hole. So here's a brief description of the treatability study. The representative soil samples were collected from the site. The site consisted of a sandy loam with 94% ash content and 6% organic matter content. All the samples were composited and PFAS in soil was measured. The procedure for that was the composited soil, 100 grams, was mixed with anywhere from 0.5% all the way up to 5% by weight of fluorosorb absorbent and 200 milliliters of deionized water. And then it was shaken for 120 hours, and then they tested the supernate. This chart on the side is just an interesting sidebar, if you will. So we talked about how the soil was analyzed for the PFAS constituents, and they're listed here under soil concentration. But what's really important to note is if you take a look at, for instance, PFHPS, that came in at in the soil showing below the detection limit. Yes, it showed up in the supernate at the or above the detection limit. Same thing with FOSA. It was at fairly high levels in the soil itself, but did not show up in the supernate. So this is something to think about when you're looking at doing any in situ stabilization. Just knowing what's in the soil may not be enough. You're going to have to look at what comes out after treatment. So continuing with this lab study, again, the mixture of fluorosorb into the soil, and this was without any cement. This was just the fluorosorb being used as the sole fixant, was anywhere from 0.5% up to 5%. And of course, they did the same dosings for the other fixants that were being tested. And if you take a look down at the bottom, there's all the particular constituents that we're looking at. PFOS was the real driver on this site. And we see that at a 1% fluorosorb dosing, 99.9% of the PFOS was removed, and at 2%, 100% of the PFOS was removed. But for 1 and 2% dosing, they all met the criterion, and that criterion was to reduce leaching and then model what the off-site wells would look like as from the reduction of the leaching from the on-site source contamination. Interesting to note, when the spec came out, it was only spec'd for 1% fluorosorb, initially only spec'd for 1% fluorosorb, because that was sufficient. However, what actually got installed was 2%, and that was more an operational aspect to make sure mixing in 2%, you could get full homogeneity through the treated soil. 1% clearly worked in the lab from a chemical fixation standpoint, but as you may know, out in the field, it's very difficult to homogeneously mix 1% of anything. So they mixed in the 2%, and the project was completed, and we're moving on to the next one. So in closing, I just wanted to talk about the current state of sediment and source control. Again, I've focused in on, the whole talk is about 2 different modified clays and how they relate to MGP sites. The organoclay is well established, Fluorosorb is new. So I just want to give you some heads up as to what's happening now in real time with Fluorosorb for source control and sediment capping. RCM with Fluorosorb is currently being deployed on the Canadian base, that same Canadian base I just talked about, only it's going into a retention pond and a swale. That is that 2% mix of stabilization of 20 cubic meters. That was this Canadian job I just talked about. The next bullet is RCM deployed for sediment capping in a stormwater swale on a US DOD facility. That wrapped up last week. A large DOD in situ stabilization and solidification pilot study was completed in July of 2018, and there's a paper coming out on that very soon. And lastly, several large field pilots are currently underway for capping and/or stabilization of sediments with PFAS. I'd not written here, but I would add there's treatability studies for organoclay on MGP sites. There's about 15 of those going on right now. And to date, they do not have a PFAS issue, or at least they're not aware of it yet. But if they do, the data, we can go back through this data and help anybody out with anything they may need. So with that, I think it's time for questions for the group. I want to thank everyone for listening, and we're ready to go. Thank you.
All right, thank you. Okay, thank you, Matt. I guess I'm gone. Oh, then we're back. Okay, guys, we're going to open it up to questions for everybody. We do have to ask that you have to use the microphone in case you got any questions for Matt, so he can hear you virtually. Okay, so I'll open any questions up for the panel from the previous discussions. Get my steps in.
Okay, I've got a couple of questions. Let's see, the first one's for Sarah. So with the real-time forensics, was the rapid analysis and the rapid data processing used to tweak the field investigation decisions in real time?
So it's on. It's on. Yes, and I'm sorry that message didn't come out clearer in the talk. Yes, so we would collect borings, at a decision point in the field, then run them through the system, the quick turnaround lab, the data analysis, the dropping them in the forensic buckets, and then use the new combined data set to decide, okay, are we done at that decision point, or do we need to, in this case, step out further upstream or downstream to find the extent of contamination?
Okay. And for the 2 different MGP signatures, the one of the zone farther to the west, and then the one for plant number 9, were those clear enough distinctions to, in real time, distinguish them?
I can't remember exactly when that story evolved. It was evolving as we went along. We pretty quickly started talking about this facility that was the coal tar facility nearby, and
Each time we added more data to the set, things became more clear, right? The buckets became more distinct. So I can't remember exactly when that decision was made, but yes, it became clear by the time we demobilized that we had a distinct difference. And it was a lines of evidence approach too, right? Like we had this facility here, we had a conceptual site model of the spills related there, the physical location downstream of the plant. And I believe the difference was mainly in the naphthalene signature between the number 9 MGP and what we were seeing in the waterway.
Okay. And then I've got one question for Benjamin, and about the surfactant enhanced fluid recovery. Has that been implemented yet? Has the surfactants been injected yet?
The pilot study has, the full scale has not.
Okay.
Yeah,
And-
pilot study was in April timeframe.
Okay. And so for the pilot study, surfactant injection, has there been any sampling to see what the change in dissolve? Okay, so with the surfactant enhanced remediation pilot study, after the surfactants were injected, was there any assessment of changes in dissolved concentrations for PAHs in the zone where the injection happened?
Yeah, so we had a performance monitoring well so I mentioned 3 treatment areas. One was just an ISCO area. One was a surfactant injection with water recovery, followed by a surfactant combined ISCO. And then one was just a surfactant ISCO. And in both of those surfactant areas, the dissolve phased COCs were still relatively high. We saw a lot of reduction in the soil, but it seemed like we didn't get all of it out of the water. It was remaining in the dissolve phase by the time we had about, I think, 3 post-remediation sampling events. And BTEC styrene and naphthalene were really we didn't do a full PAH because we didn't have those as COCs at the site anymore. Those have been removed as COCs. So we didn't have a big range of PAHs that we had been sampling for, but BTEC styrene and naphthalene saw big reductions in benzene, but as in the dissolve phase, we were still seeing similar concentrations in the toluene, ethylbenzene, xylene, styrene, and naphthalene, actually.
Okay.
Anybody else?
Okay, everyone, thank you very much. Thank you, Sarah, Ben, and Matt. Great presentations today, and we're off to our break.
Thank you.